Welcome to the second part of lecture 2 in bmb540. Here we will introduce the concept of entropy and also the second law of thermodynamics. Um, as I had previously asked you to do, you should always think why we a new need to define a new quantity or a new law. So the first question that we should think about is why do we need to spend time studying a second law of thermodynamics? Is the first law not enough? Let us look at a few simple processes. If you drop few drops of ink into a beaker of water, this ink automatically dissolves into water. But the reverse almost never happens. So the ink will not spontaneously separate from water. For most processes that we look at, um, the direction of energy determines which way a process will occur. So for example, if I push this ball along these stairs, the ball will fall down, it will not go up, because at the bottom there is low energy and on the left hand side there is high energy. So usually energy flow determines which direction a process will take. But biological systems in particular are not just determined, the direction of biological processes is not just determined by the direction of energy flow, but something else as well. Normally things go to equilibrium given enough time. But this ball, for example, will never spontaneously jump back to the higher point. So, so there is a certain unidirectionality associated with these processes, the dissolving of ink into water and the falling down of a ball. So this unidirectionality is not accounted for in the first law, which only talks about the flow of energy. Secondly, for the systems we are looking at, the first law is not enough to calculate flow of energy such as heat, work, internal energy, or state variables such as pressure, volume, and temperature. So in order to do this, we need to introduce a new state variable which accounts for the unidirectionality associated with natural processes. This we are going to call entropy. And we will make a convention that the entropy of the universe always increases. This accounts for the unidirectionality of natural processes. Note that this is only a convention. It could well have been that the entropy of the universe always decreases. But it has been adopted for a long time that the entropy of universe always increases, and this accounts for the unidirectionality associated with, for example, the dissolving of ink into water. There are various statements of the second law, and here this slide shows you two of them. The entropy of an isolated system increases during a spontaneous change. Heat does not spontaneously flow from a cold object to a hot object. One of the consequences of the second law is that all heat in a given system cannot be converted to work. Some of it is wasted. The mathematical expression of the second law is on the right hand bottom of the slide. It says that the differential change in entropy is equal to the change in reversible heat divided by the temperature, or that the differential change is greater than equal to the differential heat transfer divided by the temperature. We will come back to these equations in a couple of slides. Um, Daniel Wusner, who is your other lecturer, will talk a bit more about the molecular interpretation of entropy. But entropy is typically associated with a degree of disorder in a system, or to be more accurate, the number of states, number of configurations in a system. So the entropy is equal to Boltzmann constant multiplied by the logarithm of W, which is equal to the number of microstates. But we will not delve deeper into this molecular interpretation of entropy. You should just associate entropy with the number of possible microstates that a system can have. So with that, let's look at ink dissolving into water. So here in image B, you have three particles of ink surrounded by many particles of water. This is one microstate. You can replace the molecule on the left with the molecule on the right. That would be another microstate, and so on. But if these molecules are dissociated into water, they can adopt a much higher number of microscopic configurations. Each molecule may be in many different places, and therefore the system on the right has higher entropy than the system on the left. Similarly, ideal gas, an expanded ideal gas has a so for example, an ideal gas in a larger volume has a higher entropy than a ideal gas in a smaller volume simply because there is more space for the ideal gas, the particles of the molecules of the ideal gas to occupy. So there are more configurations they can occupy. When ice melts into liquid, the liquid has higher entropy. When ink dissolves into water, the dissolved water containing ink has a higher entropy. So the mathematical expression for the direction of spontaneity is right here, and we will derive it in this slide. So if you look at the first law, the change in internal energy is equal to the flow of heat plus the flow of work. But since internal energy is a state variable, we can take a reversible path and write this as dq reversible plus dw reversible. I can rearrange the two right-hand parts of this equation to write the differential change in reversible heat is the flow of heat plus the difference between the work done minus and the reversible work done. Now the reversible work is always higher than non-reversible work, which means that this quantity in parentheses must be negative. And if this quantity is negative, then dq reversible is always greater than dq, which means dq reversible divided by temperature is always greater than dq by temperature, or a differential change in entropy is always greater than equal to a differential heat transfer divided by the temperature. And this gives you the mathematical direction of spontaneity. I will also upload a video which will show you how to calculate some simple um, shows you some simple examples of calculating the change in entropy of simple processes like an isothermal expansion and constant volume cooling. With regards to reversible expansion, you should refer to page 328 to 329 in Korean. The first and the third parts will be uploaded in a video, the third part of the video, or third part of lecture 1. And we will discuss, to conclude this lecture, the entropy of phase changes. Now, during a phase transformation, the phases are in equilibrium. For example, at 0 degrees centigrade, if ice is melting, and if you lower the temperature a little bit, liquid water gets converted to ice. If you increase the temperature by a little bit, the ice melts into water. So the two phases are in equilibrium and the transfer of energy is reversible. And therefore, ds is equal to dq reversible by T. But since temperature is constant, you can integrate this equation and say that the change in entropy is equal to the reversible heat transferred. And since this pressure is occurring at this phase transition is occurring at constant pressure and temperature, the heat transferred is equal to the enthalpy of the transition. This transition could be melting or vaporization divided by the temperature of the transition. So this is how you can calculate the change in entropy of a phase transition. For the other processes, you can look at the video that will be uploaded, and for the reversible expansion, please read pages 328 and 329 in Korean. And this concludes the second part of lecture 2. The third part of lecture 2 will be this video which will be uploaded. Thank you. Oh, one more thing. Um, Here is a simple question. What is the change in entropy of a system when ice changes into water? Is it positive, negative, or zero? And I already gave you the answer. The entropy will increase and the change will be positive. Here is a lipid bilayer which is self-assembling. Sorry, a mixture of lipids which is self-assembling into a lipid membrane. So one should think about what happens to the entropy of the system here. Does it increase or decrease? Here is the folding of a protein. You have a certain polypeptide which is surrounded by water and it eventually folds such that the hydrophobic side chains point towards each other or are protected from water. In both of these cases, when a hydrophobic side chain or a hydrophobic lipid tail is exposed to water, the water around the hydrophobic tail is highly ordered, which leads to a low entropy of water. When the protein folds, the water which was otherwise uh, not free and was restrained around these hydrophobic side chains will now be free and can adopt many conformations, and therefore the entropy of water increases when a protein goes from the unfolded state to the folded states. The same is true for a lipid membrane. The entropy of the water increases when a mixture of lipids assembles into a membrane. However, if you look at individual lipid tails here, these lipid tails were free to move around in water. But now, inside a lipid membrane, these tails are highly frustrated because they don't have the conformational freedom that they had when they were dissolved in water. So the entropy of the lipids actually decreases. But this is overcome by the large amount of entropy associated with water becoming more free when the lipids self assembled into a membrane. Finally, we go back to the video that I had shown you earlier, where DNA was being pulled through a toxin. What you have to note here is at this point, in the middle of the toxin, the DNA is linear, it is not folded. While on the upper side of the membrane and the lower side of the membrane, the DNA is folded, has higher entropy. In the middle part of DNA, which is inside the toxin, has lower entropy. So as the DNA comes out of the toxin on one side, it starts to fold because it is surrounded by water, not confined inside a toxin in a pore. And therefore, the entropy of the DNA starts to increase in this part, and it pulls the DNA from this low entropy region inside the toxin, and the DNA is eventually in a folded or high entropy form when it comes to the other side of the membrane. And this concludes the second part of lecture